Hello everyone, my name is Biraburaj. I'm a third year PhD student in the Department of Computer Science and Engineering at IIT Hyderabad. Today I will be presenting our work titled AFGNN, API Misuse Detection using Graph Neural Network and Clustering. In this presentation I will walk you through the motivation behind our proposed approach, the problem we are addressing, our proposed approach and experimental result. Let's get started. Application programming interface, which is a set of predefined classes, interface, method which allow developers to build application efficiently by leveraging existing reusable code. Modern software development heavily relies on APIs. In particular, Java standard library APIs along with numerous third-party APIs are extensively utilized in the development of enterprise applications. But due to limited number of examples in the API documentation, official API documentation, developers often rely on online platform or generative AI for unfamiliar API. But it may introduce unintentional error because it may not conform to standard practice. So it leads to API misuse. Such misuse can lead to vulnerabilities such as resource leaks, memory corruption, and data races. If you consider this example, which is retrieved from commit history of a GitHub project, which demonstrate buffertreader.readline API methods at line number 3. If you consider correct usage in these down box, that buffertreader object BR is closed properly at line number 6, which is ensuring the proper resource management. But in contrast, here in the upper box, that closing operation is missed here. So it leads to potential resource leak vulnerabilities. This actual example of buffertreader.readline API correct use and misuse from a GitHub project highlight the occurrence of API misuse in real world code and importance of ensuring API usage correctness. So there are some techniques to detect API misuse, such as code kernel, which are giving better performance in short code, but when it handles longer code, the performance is decreased significantly. As well as we can use large language model for detecting API misuse, but their high computational cost and hard fine-tuning nature and confidentiality issues limited their practical applicability in API misuse detection. So we introduce AFGNN. It's a lightweight, efficient graph neural network framework for API misuse detection. This is introducing a novel API flow graph representation. We will be discussing what is API flow graph representation in detail a little later. So this is the overall pipeline of AFGNN. So GitHub code snippet, all API usage examples is converted into API flow graph. Then AFGNN generating embeddings for these API flow graphs, and these embedding can be utilized in the downstream task. So we are doing clustering technique in the downstream task. We will discuss the reason for clustering, choosing the clustering techniques. Via these cluster we can use these clusters for understanding different usage patterns, suggesting frequent API usage, identifying potential API misuse, and so on. So if you consider the AFGNN pre-training pipeline, so very big Java code corpus is converted to AFG. The row AFG cannot be fed to AFGNN as it is GNN based architecture. We need to give number. So that is what we are using a small language model, which is Codify. Empirically we have chosen Codify among other small language model for initializing these embedding. Then that graph is fed to AFGNN for learning. So AFGNN learning in the pre-training task using context prediction task. What is context prediction task? So using a small graph among big graph, it tries to predict big graph. So it is learning from neighbors node. So after the pre-training task, we have train weights. These train weights can be used in the downstream task. AFGNN is GNN based architecture. It supports several GNN architectures such as GCN, RGCN, and GAT, RGAT, and so on. So we have tested all those for GNN architecture, but we are presenting only two variants, AFGCN and AFRGCN, because these two are giving superior performance than GAT and RGAT. API flow graph. As I said, this is the one of the novelty of our proposed approach. AFG is a directed graph representation of a given API usage code snippet, which is a 3-tuple. V is the set of node is nothing statement level node on the code, and E is the set of edges among these node, and X is the label of edges. So AFG captures 3 types of edges: data flow, control flow edges, API call sequence edges. What is data flow edges? It represents the flow of data between the API related operations. So it captures the data flow from source node, that is variable definition, to the target node, that is usage of that variable. Second one, control flow edge. Control flow edge represent the control dependency between the API related operation, which is indicating the flow of control execution order from source node. Source node is nothing in branch conditional structural construct to the target node. Target node is nothing the statement within the bodies of construct. And third one is sequential edge. Sequential edge represent the sequential order in which API calls are made on a particular receiver object. For constructing AFG, we have implemented AFG generator, which is first pass the given code snippet into AST. From the AST, it is extracting the statement level node. Then it is adding FT, CD, SE, and so on. So this is an example for AFG. So targeted API is statement.execute. You see that line number 4, this is the corresponding API flow graph. So nodes are labeled as line number for the explanation. You consider this statement is used here 7, line number 7, and line number 8, line number 9. So there are data flow between these lines. That is what line number 4 to 9 there is a FT and another FT between 4 to 8, another FT between 4 to 7. And then if you consider these statement line number 7, statement not equal, if statement not equal null, then only the statement 8 and 9 will be executed. So from 7 to 8, 7 to 9, control dependency is there. So that CDHS is added, 7 to 9 and 7 to 8. Okay, now we come to sequence edge. Here, this connection.create statement should be invoked before this connection.close, because that is the order, right? So SCHS is added between 4 and 11 here, but not 3. Why? That is different object. That is what I said earlier. That is specific targeted same receiver object. This is different object. Okay, now what is the difference between row API and pruned API flow graph? So at the inference for a given targeted API of interest, full complete graph is unnecessary, because in multi API setting, here you see driver manager.get connection is one API method, statement.execute is another API method. Our targeted API method is this. So these related nodes and edges are not necessary. It is introducing noise. We have tested with full graph and pruned graph. So that is what we introduce one pruning algorithm. Our pruning algorithm remove all the unnecessary edge from the API flow graph. It retains only the node which is reachable from O to the targeted API only. So AFGNN generate embeddings for the API usage example. Why we have chosen clustering for detecting API misuse? Pre-work has shown the frequent pattern in the real world projects often corresponding to the correct API usage. That's what we are using that clustering technique. Our hypothesis is large cluster indicate frequent or common API usage pattern. Smaller clusters indicate infrequent or potential misuse. So experimental setup, baseline, we have conducted two type of experiment. One is the evaluating the performance of clustering technique and evaluating the performance of misuse detection. So for clustering technique, we have chosen two baseline among other baseline because these are giving better performance. And for detecting misuse, we use Misuse Detect and graphic misuse. Dataset for evaluating clustering technique, we use code kernel dataset. We manually labeled because there are no any dataset labeled dataset for clustering technique. And MuBench is popular real world benchmark for measuring the API misuse detection. Metrics used, we used RAN index and mutual information for code kernel. It means clustering techniques, because these RA and MA are measuring the similarities between predicted cluster and ground truth. And for MuBench detecting API misuse, we use accuracy, event score, recall, and precision. So if you consider the result of AFGNN in the clustering task, AFGNN is giving better, superior performance and surpassing all the baseline. Why AFGNN giving better performance than AFGCN? Because this is relation. It is considering the control flow, data flow, and sequence of edges. That is what it is giving superior performance, and it's surpassing all the baseline. And in the API misuse detection on MuBench, we consider these baseline. AFGCN is giving superior performance than the baseline, and it is giving around 12% improvement. And kind of application study, we studied what about the impact of SCHs, adding SCHs and removing SCHs, sequential edges. So adding SCHs greatly boost AFGNN performance, increasing RI by 48% and MI by 40%. So conclusion, AFGNN use AFG by including data flow, control flow, and API call sequence. That is very, very important in the AFGNN performance. And it is learning from vast open source repositories, and it identify pattern via frequent API usage pattern by clustering, and it is showing superior performance. It's surpassing all the several baselines, and AFGNN is also more efficient and less resource intensive. Thank you for watching, and if you have any questions or would like to know further about this research, please feel free to reach out, and by scanning this QR you can access the artifact. If you want to contact, you can scan these QR, you can get all the contact of me. Thank you.